How come my car is strong here, but brittle here? This is a real-world example of a chemical reaction called corrosion. According to the Association for Materials Protection and Performance, the estimated global cost of corrosion is $2.5 trillion US. This highlights how such a seemingly small environmental reaction poses a great threat to modern-day engineers. Let's talk about what corrosion is and how it impacts our everyday lives. Corrosion occurs when water molecules ionize and create hydrogen and hydroxide ions. This process is fairly slow without any accelerants, as iron needs to transfer electrons to these ions to form products. Salt speeds up corrosion by turning the water into an electrolyte, making it more conductive. This increases the likelihood of iron losing electrons to hydrogen or hydroxide ions, leading to the metal deteriorating. This doesn't look dangerous, but in a few moments, it's going to start destroying itself. This is corrosion in real time. To demonstrate this process, I will be simulating an intensified example of natural corrosion by using hydrogen peroxide, steel wool, and salt. Why steel wool? With its string-like structure, there's a great amount of surface area and exposed iron. Why hydrogen peroxide? It ionizes as hydrogen, hydroxide, and oxygen, all posing as ions for the iron to bond with. With more oxygen, there's a much faster wait time for the oxygen in the surrounding environment to aerate into the solution. Now, salt does not create rust on its own, but by adding it, it's turning the water into an electrolyte as it dissolves, allowing for electrons to move more easily in the solution. Additionally, the chloride ions disrupt protective layers that may slow rusting. This is why we see rust thrive in scenarios such as ships in saltwater or cars in winter climates. As soon as this touched the solution, tiny electrochemical reactions began to commence. Iron atoms lose electrons, oxygen takes them, and rust forms. This is the same process that slowly weakens bridges and trains. So when we turn back to the original question of why my car was structurally strong in the front of the wheelhouse and brittle and crumbling in the back, the answer lies in chemistry rather than poor design or maintenance. Corrosion may seem subtle, but its consequences are anything but. Whether cars or bridges, this chemical reaction dictates the lifespan and safety of these structures that we depend on. Understanding this process is not just a chemistry lesson, but a rising critical engineering challenge.